Okay, so we know how an electric field will affect a charge placed at a particular location. We know how to calculate the force given the electric field, or how to determine what the electric field is given the force. We want to know now what causes the electric field in the first place. And as we said before, it's got to be other charges. Other charges elsewhere in space are creating an electric field, setting up an electric field in space, such that that field can exert forces on other charges. Okay? So this comes back to the idea we talked about on Monday, which is sort of the central theme that comes up over and over again. Charges create fields, and then fields affect other charges. So we actually dealt with the second one first, okay, when we're talking about the electric field. This is F equal to Q times E is telling us how fields affect other charges. We want to now think about how a charge creates a field. Well, we said that the electric force, and I'm just going to look at the magnitude of this electric force. So we can say the force on charge 2 due to charge 1, just to be really explicit here. If I have two charges, in fact, let's draw them here. Here's a positive, Q1 and Q2. And we said the force on Q2 will be that way. We said that with some constant times the charge, and since this is an absolute value, I'm just going to look at the magnitude, Q2 times Q1 over the distance squared. Okay. Well, now I can use this and the definition of electric field and think about if E1 is equal to F2 divided by Q2. If I divide this force by Q2, I get a constant times Q1 over R squared. Okay? So it's just that magnitude of the electric force divided through by the charge that's causing that electric field. That only gives us the magnitude, though. It doesn't give us the direction. So we want a more formal expression to give us both the magnitude and direction, the vector expression for the electric field due to a single charge particle. So electric field caused by or due to a charged particle. Or sometimes you'll hear me say the field due to a point charge, because we're making the approximation that these charges are very tiny and basically are point-like objects. Okay? Electrons really are, as far as we know, point-like objects. Okay? Larger particles like protons have some structure to them, but we can often approximate them to just be point-like. And let me just write out the expression, and then we'll kind of pick it apart. This electric field due to a point charge, I'm going to write it this way, as E1 equal to this constant, which I'm going to write this way, 1 over 4 pi epsilon 0 times Q1 over the magnitude of R vector squared times R hat. Okay? So what are the pieces of this expression? Well, first off, we have a constant. This 1 over 4 pi epsilon 0, for historic reasons, it's written this way, and we'll see more connections with it later in the course. But for right now, just think of it as a number. And it's approximately equal to 9 times 10 to the 9th, and the units are Newton meters squared per Coulomb squared. Okay, so it's just a constant. Q1 is We're often going to refer to that as the source charge. Source meaning it's what's causing the electric field that we are observing. Okay? R is a relative position vector it points, erase some of this here. R points from the source charge to what we're going to call the observation location, meaning where are we measuring this electric field? The point in space where we want to find the electric field. So mathematically, how would I describe that? If I want a vector that points from one place to another, I have to do what? Subtract them, right? And so which one goes first? The position of the final, right? So it's from the source to the observation location. So this is R final, or R of the observation location, minus R of the source charge. Okay. There's a lot of R's floating around here, but this means the position with respect to the origin of the observation location, this position with respect to the origin of the source charge. This is the relative position vector that points from one to the other. Okay. And then what's R hat? That's a unit vector that points in the same direction as R, right? Okay? So let's see how this works. First thing to notice is that all of this, everything here, except this R hat, is a scalar, right? This is just a positive constant. That's just a number. We're dividing by the magnitude squared, so that's just a number. That's positive, but Q could be positive or negative, okay? So this thing out front could be a positive or negative scalar multiplying a vector. So let's look at two different cases. Here is a source charge. Let's say it's a proton, for example. Call this Q1, and it's greater than 0. And let's say I want to find the electric field created by this source charge at some location A. Let me pick this as my location A. Okay. First thing I have to do is draw the R vector. The R vector is going to point in what direction? Everybody point with your fingers. Up like that, right? From the source to the observation location. So that's R. And therefore R hat, same direction, right? So this R vector always is pointing away from the source to the observation location. Let's look at what's multiplying R hat. This is a constant that's positive. We're dividing by a magnitude squared that's positive, and Q1 is, in this case, positive. So I'm going to get an electric field that points in what direction? Away from the charge, right? In the same direction as R hat. And when I draw it, I want to draw the electric field, and this is important. Draw the electric field vector with its tail at the observation location. Okay, so E is pointing that way. For example, yes, question. Okay, so the question is, what does epsilon 0 stand for in the constant? It itself is just another constant, and you could work it out from here, but it turns out that epsilon 0 is equal to 8.85 times 10 to the negative 12 Coulomb squared over Newton meters squared. Okay, it's just another constant of nature. It's just called the electric constant. Okay. Other questions? Okay, so let's think about another observation location. Let's imagine let's call this location C. How much time we got? We've got some time, good. Let's call this location C. The R vector in this case points from where to where? starts at the source and ends up at C. Okay, so the R vector in this case points there, which means R hat points same direction. So I'm taking this positive constant and a positive charge and a positive magnitude here, all multiplied by R hat. So the electric field that I would draw at C points same direction as R hat, right? Points away from the electric field, or points away from the source charge. So what we see, and you could do this for various different locations, and what you would start to see is a pattern that looks kind of like this. Let me just show a little VPython program. So what am I showing here? I'm showing, let me just clean it up a little bit to start. What we have here is a positive charge, a proton for example, and at various observation locations that I've just laid out in two concentric circles around the charge, I'm measuring and plotting the electric field vector at those locations. Okay? And everywhere I plot the electric field, at this location, here, 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 and so on, the electric field due to or created by that positive charge is pointing away from the positive charge. Okay? I plot it out here. It's pointing in the same direction. Why is the arrow smaller? You're farther away. If I'm twice as far away, what happens to the electric field? It's a quarter, right? It's 1/4 of what it was before. Okay, so the electric field drops off with distance squared. I get twice as far away. The field goes down by a factor of 4, but the direction stays the same. Okay, it's always going to be pointing directly away from this positive charge. What would happen if I changed the sign? What if I was looking at the field due to a negative charge? It would point towards. That's right. Let's take a look. So we get something that looks like that, where at all these observation locations, the electric field is pointing towards that negative charge. How does that work? Well, let me change the sign of the source charge here. This is now a negative. My R hats and my R directions stay the same for these observation locations, right? This is A and this is C. But now I have the R hat pointing away. This is a positive, this is a positive, but Q1 is now negative. Multiply a negative by a vector and you get a new vector that points in the opposite direction of R hat, right? So if R hat's pointing that way, my electric field is pointing in that direction. My electric field here is pointing in that direction. Okay? Do we see how this works? Is this making sense? Let's try a couple questions just to see if we got this. The first one is we have an electron placed at location A, and the observation location is B. So we want to find what is the direction of the electric field at location B due to the electron. And we find that the electric field has got to be pointing in direction 8, right? Because the electron is essentially what we just drew here, right? The electron is at some location A. So the source is at location A. The observation location is at B. And so if you drew R hat always points towards the observation location. Multiply the negative charge by that R hat, and you get an electric field that points opposite to R hat towards the source, and that's the electric field. Okay? So in general, you should just keep in mind, electric field due to positive charge points away from the source. Electric field due to a negative points toward the source. Okay, just a good rule of thumb to keep in mind when you're reasoning about electric fields. And you start to see already that in this course, this sort of qualitative reasoning particularly about directions, becomes extremely, extremely important. So if you had any trouble doing this today, you want to make sure you get this down pat. Okay. We have a couple minutes. Let's try a quantitative example in the time we have remaining. So let's say we have a charge at the origin, and let's make it something different this time instead of just a proton. Let's say it's some small object that we can treat like a point, and it has a charge of 3 times 10 to the minus 9 coulombs. Okay, so it's the location is the origin here of this axis. And let's say our observation location A is at 230 meters. Okay, so we want to find the electric field vector due to this source charge at location A. Okay, so the first thing we need to do is find R, and we say R is the position of the observation location minus the position of the source, but the source is at 0, 0, 0, so R is just going to be what? 230. Okay, we have 230 minus 0, 0, 0 gives us back 230. Okay. We want to find R hat, so that means we're going to need the vector and the magnitude. The magnitude is going to be square root of 2 squared plus 3 squared plus 0 squared meters. So what's that work out to be? We have square root of 4, or square root of 4 plus 9, or square root of 13 is 3.6. Thank you. Okay? And then we need R hat, so we're going to have 2 divided by 3.6, 3 divided by 3.6, 0. And that gives us something like, I think it's 0.55, comma, 0.83, comma, 0. And you can check me if I did my math right. Okay. Next, we've got the R hat, so now we have to do is just find this scalar part. The scalar part is 9 times 10 to the 9th times 3 times 10 to the minus 9 divided by 3.6 squared, which is going to give us back 13. Okay, and that works out to something. I think it works out to about 2 or 2.1 newtons per coulomb. Finally, we just multiply that scalar part by the R hat, 2.1 times 0.55, comma 0.83, comma 0, and the units are newtons per coulomb. And if I did it right, I think it works out to be 1.15, 1.730 newtons per coulomb. Okay? That is pointing in what direction? Up and to the right, right? Away from the positive charge. So another thing that you should get used to doing is checking your answers by looking at qualitatively what should happen. We know the electric field should point away from a positive charge. We get a positive x component, a positive y component. Looks like this agrees with what we expect. Okay? All right. We will have a short practice quiz on Friday just to get us used to having quizzes. We won't grade it.